right, so welcome to topic 8.6. This lesson I'm going to divide into two videos. Remote students, I'm going to have you work on this over a course of 2 days so we can have a Google Meet in between. For this particular session, you do need some resources, periodic table with charges, polyatomic list, and then you'll need this handout, which is like the activity series for single replacement, but you need what's called a solubility table for double replacement. Double replacement, we can like I said, we're going to divide it into two pieces of how we work through in predicting products, and there's something else we have to look at when we predict products for double replacement. Double replacement is, again, a lot of times mixed up with single replacement. Again, the single part of single replacement means a single element, typically a metal, but it can be a non-metal, exchanges itself with again, if it's a cation, it exchanges itself with a cation, so a metal for a metal, or a non-metal for a non-metal, or anion for an anion. It just depends on, again, what you have in terms of reactants. Double replacement, we have two compounds, and so we have an exchange of a cation for another cation, resulting in two new compounds forming on the product side. So double replacement reactions tend to have a slightly different outcome in terms of what they produce. Typically, a double replacement reaction forms what's called a precipitate. I'm not talking about precipitation as in rain or snow. I'm talking about a precipitate in terms of a solid that is formed due to the exchange of these ions taking place, and a solid settles out of these two liquid solutions. So if a precipitate is not formed, sometimes water or a gas can be produced. If neither water, a precipitate, or a gas is formed, like a single replacement reaction, it's considered a no reaction. So there are steps in which we go through to determine the products. We have to assume that all double replacement reactions are going to take place. We don't look at the activity series. That's only used when you are comparing a single element to a cation or anion in a compound. So right out of the gate, we have to assume all double replacement reactions occur. So the first thing we need to do in order to predict products is we have to ultimately figure out what is exchanging with what based on charges, what are the resulting subscripts, and then balancing accordingly. So I have an example that works through it, breaking it into those said steps. So we have these two reactants, and I'm also going to include these two subscripts here. And so one thing we talk about with double replacement are phases of matter. So if you see a subscript AQ, that stands for aqueous. Aqueous means that you have ions present and it's dissolved typically in water. So for example, if you take table salt and put it into water, you no longer have salt. You have sodium ions and chlorine anions in a solution of water. That's an aqueous solution. The other ones that we see, we use an S for solid. We use G if something is a gas. And we use L for liquid, and that's going to become important here in a few moments. Okay, so when you go about the process of figuring out your products, the first step that I work through is I separate my reactants into their ion form. So I know that I have my cation and anion here, so I'm going to split these apart. Cation and anion, I'm going to split those apart. So I have my cation is lead. Using the periodic table, I do not know the charge of lead, but I do know, using my polyatomic list, that NO3, my anion, is a -1. Therefore, that means the PB is a +2 charge. Splitting apart my other reactant, I have potassium is my cation. It's an alkali metal, and so it's a +1 charge. It's combined with an anion of iodine, which is a -1. So that tells me what my reactants are going to do when I dissolve them into water and make them into an aqueous solution. So what I'm looking at is what is going to result when I combine these two together on the product side. So what we do is we switch the partners. So what you do here is, like single replacement, you switch like charges. So the PB and the K are what are going to exchange. So what results here is I have PB with a +2. It is now going to combine with the iodine that has a -1 charge. My other product is going to have the cation potassium. Again, your cation always goes first. It's now combining with the nitrate, NO3 -1. So now I'm at the point in which I want to figure out or write the formulas for my products. And so I do that by crossing charges. So the formula for my first product is going to be lead 2 iodide, or PbI2. My other product, I have a +1 -1. So my other product is KNO3. So from here, I now know my reactants, I now know my products. I can work on writing a balanced equation. When I get to that point, I'm going to make my spots for balancing, and I have my reactants up here. So I have PB, NO3 aqueous, meaning again dissolved in water, writing it as a subscript, combining with another aqueous solution, Ki, which is again aqueous. My resulting products are what I've rearranged up here. Order doesn't matter. I'm just going to write the PbI2 first. I'm going to put a set of parentheses, but I will talk about state of matter here in a second, plus KNO3. Ignore my scribble there. So from there, what I have going on is I now have my reactants and products determined. The next thing I need to do is balance my reaction. I can see I have 2 NO3s, so a 2 is necessary on the product side. I now need to add a 2 in front of the Ki, and I now have a balanced reaction. In order to determine did this double replacement reaction happen, one of 3 things need to happen. It needs to either make a precipitate, water, or some kind of gas. So neither one of these is water. And so what I need to do is look at the solubility table that's attached as another handout to determine the phases. So when I take a look at this, let's see here, there we go. If you take a look, these two are the exact same thing. They're just different ways in which they're sorted. This one's sorted alphabetically. This one's sorted by solubility. You can use either one. You're going to get the same answer. So what you do is you find your 2 ions in your product, Pb and I. So your cations are across the top. Your anions are down the left-hand side. You find where the 2 intersect. Where you find the intersection, you find the letter X. X stands for not soluble. Again, not soluble means that it is not able to dissolve in water. That means that is going to settle out as a precipitate or a solid. So what we're going to do here is put an S for solid. We now find our other product, KNO3. Using the top table, K is right here with potassium. Finding NO3, followed across, I find an S. S stands for soluble. It means that it is able to dissolve. So it's going to stay as ions in the solution. So we're going to write AQ in its parenthesis set. So basically, I did this step right here just to save us from having to rewrite it. And this is how you work through a double replacement and determining the phase in which your products are formed. So I have 2 more examples that I want to work through in this video. And that's starting here with AgNO3, aqueous combining with sodium chloride, aqueous. So following the steps, the first thing you do is you separate your cations and anions. So we have our 2 parts here are cation being the silver and NO3. Again, going back to our days of chemical naming, when you utilize your polyatomic list, NO3 is a -1. Because I don't see any other subscripts in this formula and that 3 is part of the nitrate, that means silver must be a +1. So then when I look at my other reactant, sodium chloride, I have Na and Cl. Both are found on the periodic table. Sodium is a +1, chlorine's a -1. Now you're looking at what's going to exchange. Again, like charges are what's going to exchange. So I'm going to work on figuring out what is the formulas for my products now. Silver is now combined with chlorine. Sodium is combined with nitrate. One thing I see a lot of times students see is they see this NO3 first and sodium second, so they write NO3Na. You don't do that. Again, proper formula writing, you always put your cation first. So Na is a +1, NO3 is a -1. So when we go to get our final formulas here, I have AgCl and NaNO3. Again, when it comes to order in terms of your product side, you could put NaNO3 first, and I'll just do that to show you some variety. So we have NaNO3. I'm going to again set up my parenthesis here, and I'll come back to that in a second. And my other product is AgCl. Okay, so it looks like it's already balanced because we had +1, -1s on each side. So everything's balanced. So that was an easy thing to take care of. So now the last thing is just the solubilities in terms of these two products. So when you take a look, we have sodium and nitrate. So we have nitrate here, we have sodium, you find where they intersect. We have an S for soluble. That means we are going to write that that is aqueous because it is able to dissolve within water. AgCl, so sodium, or excuse me, not sodium, but silver chloride. So here's silver. We have chloride, find where they intersect. There's an X there. That means it cannot dissolve within water. So when these two ions combine, they are going to settle out as a solid precipitate in the bottom of a beaker or test tube. We are then done with example 1. Last example for this video is combining an acid with a base. So we have HCl, separating things out. We have hydrogen as our cation, chlorine as our anion. Looking at our periodic table, hydrogen's +1, chlorine's a -1. Our second product, our second reactant, I really should say, not product, we have lithium, and we have a polyatomic OH. Using our periodic table and polyatomic list, we established +1, -1. Again, we know the exchange is going to take place between like charges. So we need to work on determining what are the formulas for our products. So we have HCl +1, -1, and then we have H is now combining with the OH. So we have H +1, OH -1 is one of our products. Our second product is going to include the chlorine and lithium. Again, cation always going first, therefore lithium +1 combined with chlorine -1. Last step here is you cross to get your subscripts. So we have a +1, -1, so HOH, LiCl. Hopefully you see something kind of funky going on here. HOH is another way of writing H2O. So this reaction is a little bit different than what was up above in that we now are making water in this particular example. So like we've done so far, we're going to go ahead and fill in our products. So one of our products was water, H2O. You can write it as HOH. Either way is fine. So you can have H2O or HOH plus that lithium chloride. So if you think about it, we said HOH is water. You're not going to look for water on here because guess what? It's going to find a dash there. Think about it. Is water dissolvable within water? So when you have water as a product, you're not going to look at does it form a precipitate because water is not going to precipitate out in itself. So what water is at room temperature is a liquid. So we are going to put L for liquid. The last thing we just want to check is the lithium chloride. So we find lithium here, find chloride, find where they intersect. There's an S for soluble. So S for soluble means it's aqueous. And that's the last thing, is a lot of times students see this S and they think that means solid. When you're interpreting that table, the S stands for soluble. Soluble means it's able to dissolve. We represent that as aqueous. So this does mean a reaction took place because a liquid formed. So in the 3 examples, we had 2 examples with precipitates forming, this third one with a liquid forming. And this is how you predict products and use a solubility table with double replacement reactions.